Hey everybody, my name is Trevor. I work at Hyperlane. I'm the back-end team lead there, so kind of all this Rust infrastructure that powers a lot of the delivery of messages, that's what my team does. Today I'm going to be talking a little bit about just what Hyperlane is. I'll give like a brief overview of like the architecture, what we do, what problems we solve, and then chat a little bit about some recent work that I think is pretty exciting around using EigenLayer for economic security for messages between two different chains. So just to give some background on the motivation for Hyperlane, we are a modular and permissionless interoperability protocol. And what this allows you to do is just essentially send messages between two different chains. You can build applications on top of this messaging that like natively span multiple chains, whether it's EVM, Cosmos, Solana, pick your chain. Yeah, the motivation for this, I guess taking a step back and looking at some of the history, at the very, very beginning, we had a pretty homogeneous view or architecture of blockchains. It started with Bitcoin, then we had Ethereum. There was kind of this new wave of smart contract style L1s. There was no solid story for scaling that we have today, but a bunch of alt L1s were created that were EVM compatible. And this was still like a pretty homogeneous environment, but slowly getting more specialized. And then there's the app chain movement where you have these chains that maybe don't even have a VM. They're tapping into like consensus layer changes, protocol level changes to try to extract these new like novel protocol level features. You're seeing that with rollups today, and you're seeing all these different types of chains that each have their own little flavor of what they're trying to do best. And this posits a problem where if I'm just a normal user, now I kind of need to know what all of these different quirks are for all of these different chains. I need to have different tooling, different wallets. If I'm a developer, it's even worse. There's a reason why most people are just EVM developers. It's because it's easy to do and you can kind of bring it most places. But if you do anything like outside of that or want to go to other chains, that's where things get a little bit tricky. Even just managing token balances across all these different rollups, I have ETH in like 20 different places, total pain. And yeah, interoperability is an interesting one because a lot of the solutions for this rely really heavily on like consensus layer or protocol level details of these chains. So you can have amazing security between two chains by tapping into the specific features of the consensus algorithms of these chains. And you can spend a lot of time and money to build something like this, but it's not very transferable. So there's this kind of trade-off of spending time solving security problems when it comes to interoperability that tap into the specifics of chains. And that provides a tension with wanting to be in as many places as possible. So what we do is we noticed, hey, security between chains when it comes to interoperability is almost an unsolved problem. And today, developers want this. Today, users need this. And our solution was to decouple the transport layer and the application layer. So what this means is there is a single on-chain interface for sending messages from one chain to any other chain, whether it's from EVM to Solana, whatever you want. And the security for these messages is not baked into the interface that you use. So if I'm an application, I can continue sending messages through this single contract, we call it a mailbox, to whatever chain I want. And as new security options come out, I can update that. So applications can opt into what security they want without the protocol dictating what they need. So this provides, a consistent application interface for messages. If you want to develop an application today that's only on the EVM, but you have plans to go to other chains, you can do that really easily with Hyperlane. If you're excited about a ZK proof that's coming out, for Ethereum consensus, but it's not available today, you can build today, add it later. You can also do cool things like having the security scale with what the message content is. So let's say you're building a bridge, you might want cheaper security for a message that is only transferring $5, but more expensive security for one that's transferring $1 million. So you can kind of dictate the level of security you want depending on what exactly you're doing. And this kind of just leans into the general ethos of being maximally composable, developer first, and modular, in that like we have this single protocol that doesn't enshrine what applications want to do. yeah, this is kind of more on that. Like you can configure what security preferences you want. We have kind of these like little Legos of security modules, which is what we call them. Where as an application developer, all you really need to do is just configure some on-chain things, on-chain contracts that you can provide, or we provide, and you get kind of different flavors of security. So we have like a single interchain security module, which is a contract that defines this function that can verify proofs, whatever you want, for the validity of messages. And we provide like some little Legos of how to create those, which is nice. And modular interop is the one interface to message and secure them all. So meaning we've kind of made these like really specific design decisions, so that way we have this like single immutable protocol, and you can build all these cool things around it as crypto evolves. So more specifically, this is what the architecture kind of looks like. So on the origin chain, we have a sending contract. You would encode whatever message you want. So at its core, it's really just like bytes over the wire between these two different chains. And you can build these like abstractions, applications, bridges on top of it, whatever you want. This message gets put into a Merkle tree on chain, similar to how the ETH like original ETH 2.0 like deposit contract worked. And again, we don't really like require a specific model of security, but we have this commitment, which is the Merkle root, including all of these messages that you could have a ZK proof of. You could have people signing this, whatever you want. But the gist is, on the origin chain, messages go into this thing. A commitment that attests to all these messages is provided. You need some kind of proof to the validity of this commitment, and then this is provided onto the destination chain. And then ultimately, this is sent to the recipient. So we run this like off-chain infrastructure that will deliver these messages to the recipient. So from your perspective as an app developer or a user, you're just interacting with the origin chain. We handle the rest when it comes to delivering this message to the destination chain. Okay, so getting a little bit more into the weeds of the first thing I alluded to, of some exciting things we've been working on. You know, we're not prescriptive about the security model that people use, but it is still important to provide really solid security as the default mechanism. So today, the default security we have is closer to like a proof of authority set. And again, applications, they can opt into whatever they want, but we make it easy for people to run these validators that sign these messages. And if these validators all agree on the validity of a message, then a message is considered fine. But what gets even better, or the next iteration of this, is you want that proof of authority set to have something at stake. So if they commit fraud, if they say that a message occurred that didn't actually occur, something bad should happen to them. Without this, they can kind of commit fraud and they get a slap on the wrist, or like, you know, social slashing is what people often say, of like, you know, my reputation is on the line as running one of these things, but putting real money on the line is kind of more in the crypto ethos. And this is what the proof of stake bit here looks like. So these validators, they're signing these message commitments. Their signatures are used for the verification on the destination chain, and they have stake that's up for stake. Okay, so what does this actually look like? Like, how do we slash these validators? So one interesting thing is we have a really nice slashing condition on the origin chain. So I mentioned earlier, when you dispatch a message, it's put into this Merkle tree. And you can trustlessly verify if a validator has signed a message that was not included in this Merkle tree. So we have a deterministic 100% slashing condition on the origin chain. Like, the root of the whole problem is, how do you kind of prove this on other chains, and that's what interoperability is. But we have this very nice slashing condition, and we can have an observer be responsible for looking at the signatures of validators and provide to this proof of stake contract, hey, Alice just committed fraud, let's slash her stake. Some cool things happen when you compose this with EigenLayer. So if you're not familiar with EigenLayer, it allows the ETH that's being used already for validating Ethereum to also be used by other applications for security. And there's like a huge ecosystem around this. There are these things called AVSs, which I think stands for like actively validated Stakers, yes. And we recently released this. There's a whole LRT ecosystem of these like different versions of ETH that have these eigenlayer operators. But the general idea is on Ethereum, you have this ETH that's put up as stake. And again, in the model I just described, you would only be able to have like a deterministic slashing condition on Ethereum. So that means that only outbound messages from Ethereum will have really good security, but the other ones, things get a little bit iffy. You don't have like a 100% slashing condition. But an interesting observation is you have also Ethereum rollups, which have their native bridges. Rollups themselves are defined by their bridge. So if you have a rollup that is settling to Ethereum, they have this trustless bridge. And this means that you can have the proof of somebody committing fraud. Let's say you're sending a message from rollup A to rollup B. You'd be able to still have this stake live in Ethereum by letting me prove to, on rollup A, the slashing contract, hey, Alice committed fraud. Let's send this trustlessly down to Ethereum that Alice committed fraud for her origin message from rollup A, and then slash Alice. So we kind of get the same level of like 100% deterministic, really good slashing conditions now from origin chains that are not just L1 Ethereum, but L2 Ethereum. So that's kind of it on the economic security part. We have some recent work that we've done there that I think is super exciting. I think there's like opportunity for you guys to kind of hack around this, which could be cool. Now I'll just talk briefly about some other kind of abstractions and things that we have like out of the box that could be cool to use as well. So warp routes are our play on token bridging. And again, we're not prescriptive about the security model for token bridging or any kind of usage of Hyperlane, and warp routes also lean into this. So we offer the ability for you to just deploy out of the box tokens that are bridged, whether it's NFTs, ERC20s, XERC20 as well. And you can specify what security you want for these chains, or these messages when bridging. So we have a UI that you can use. We have a bunch of tooling to let you deploy these yourselves. So if you're looking to maybe support another chain that's here, maybe build out some kind of like proof of concept of bridging for them, like this is a whole self-service thing that you guys can play around with. You can also, we have this like yield-bearing version of this, so you can have maybe like when I'm bridging my ETH, it gets locked into a contract. That contract is generating yields, and then that yield gets shared amongst all of the people who have bridged, which is pretty exciting as well. We also have interchain accounts and interchain queries. So these are two abstractions that are kind of borrowed from the Cosmos ecosystem, also known as ICAs and I guess ICQ. And what these do is, in the first case, interchain accounts, let's say I live on Ethereum, I have a balance on Ethereum, but I want to own assets on other chains. Maybe I have a Gnosis safe on Ethereum. I don't want like, signers to have balances on all these other chains, submit transactions themselves. You can have your origin chain sender control what's essentially a smart contract account on the destination chain. And you can even have this cross between like EVM and CosmWasm, which is pretty cool. Interchain queries, this is, let's say I'm on Ethereum, there's some kind of like important state that lives on Avalanche. I can use an interchain query to receive that information back on Ethereum. So this would be useful for like oracleized data, maybe like an identity provider that lives on a certain chain. You want to bring it onto another chain. Another thing worth mentioning for all of these things, like a big differentiator for us, is anybody can deploy Hyperlane onto whatever chain they want. Anybody can deploy these kind of contracts on whatever chain you want. So if you're even spinning up like a DevNet, running Anvil locally, you can do this really easily. We've recently made some steps to make this even easier with like a more friendly kind of CLI. So yeah, this kind of leaning into like one of our big things that we say. So our design is modular and it works really well with the modular stack. This is kind of the typical like, Celestia perspective on what comprises of a blockchain. And we posit that adding interoperability to the top of this is our biggest contribution. So come build the modular expansion with us. We have an office in New York, London, we're hiring. We have a bunch of bounties. Come by the booth if you haven't already. We have swag, QR codes, list of what the bounties are. I'm an engineer, and with other engineers here, we're willing to help. And I think I have like maybe a minute or two for some questions if you guys might have them. Any questions? I'll go with no. Well, cool. Come by the booth, and yeah, happy to chat. A demo for it? Yeah, so we have a bunch of documentation about it. I'd say like no guides, but well, we have a guide if you were an operator, but this is targeted for like, I don't know, the validator operators of the world who want to actually like run one of our validators and earn rewards. But yeah, come by the booth and we can chat more. Cool. Thank you very much, guys.